Hello. Today we are going to look at how graphs of different functions relate to each other. So if we start out with a graph like x squared, how does it relate? What has changed if we get g of x being x squared plus 2, and so on. We'll look at a few different examples and then see how we can play through a question ourselves. Now, if we start off with our first one, the simplest case for most ways of looking at things is if we start out with f of x is equal to x squared. We have a smiley face type function. It's a positive quadratic with a repeated root at the origin. Now what happens if we add 2 to that? So if we have a new function g of x is equal to x squared plus 2, this is effectively g of x is equal to f of x plus 2. That would be another way of writing this that relates the two graphs together. And what is going on here? Well, we have added 2 to every y output. We've added 2 to every y output. So we had our blue curve here, and every single point here has been moved up by 2 in the y direction, plus 2 in the y direction. They've all moved straight up by 2 because we've added 2 to the y output of the original function. If we subtracted 2 or subtracted 3, we'd move all of the y outputs down by 2 or down by 3. So that is our starting point. If we look at the constant on our function, or if we add or subtract a constant to our original function, we're going to move straight up and down by that amount. And any point that would be on the curve would be the same. So if we have the point, I haven't drawn this wonderfully well, but if we had the point 1, 1 on our original curve, we'd move everything up and we'd have the point 3, 1 would be on our new curve. I'll just write that in. So this would be, sorry, 1, 3. What am I saying? We originally had the point 1, 1. All of our points move up by 2y. So the corresponding point in g of x would be 1, 3, because we've moved up our y by 2. Now, the next type of situation comes up a lot when we are dealing with functions that are in the completed square form, where we have the variable part inside of a square. And the easiest version of that is where we just have the squared part by itself, so we don't have any constant added on that would move it up and down. Now, what we look at here is effectively where the root is, or more generally, where the max or min of our function would be. Because when it's in completed square form, we can very easily tell the x value of this point here, the minimum, and the x value of this point here, the minimum of g of x. So if we start off with our original function, f of x is x squared. I've drawn that in dashed here to try and make it as distinct as possible from the other two. So we can see that it has its repeated root, its minimum point at x is 0. Now, if we had, that means that it has dropped down to y being 0 at x is equal to 0. Now, if we had g of x is x plus 1 to be squared, what ends up happening is that we are looking for where this would equal 0. So where is the bit in brackets going to equal 0? Well, that's going to happen when x plus 1 is equal to 0. Rearranging, that's going to happen when x is equal to minus 1. So something that is a little bit counterintuitive is happening here. When we add on a constant inside of our squared part, instead of moving to the right like we would usually think of for adding, we end up moving left, because we are looking for where the squared part would equal 0. Where would x plus 1 equal 0? Or in h of x case, where would x minus 2 equal 0? Well, that's going to happen when x is equal to 2. So this is something we have to build up some intuition for, that when we are adding on a constant inside of our function like this, we are going to end up moving to the left, we are going to move in the negative direction, and we can see why, because we are looking for where this new input is going to equal 0. So that's how we can figure out our situations that are in a completed square form. Why are we moving the way that we are? And again, this is the simplest version of it. They can, in theory, give you ones where you're not sitting along the x-axis. You could have a constant added on here, but we already know what constants do. They've just moved us up and down. If we're in completed square form, to figure out where the minimum is, we'd still just be looking, or the maximum if we had negative quadratics, we would just be looking for where the bit in the bracket squared would equal 0. Now, the next one we've touched on several times for curve sketching, and that is when we are multiplying our function by a constant. So I have two functions drawn in here. F of x is 2 times x minus 3 to be squared, and I can see the root of that function is going to happen when x is equal to 3, because I'm looking for where the squared part is going to, sorry, the minimum of that function is going to happen when x minus 3 is equal to 0, just like we talked about here. But if we multiply that by 2, that means that whatever this original function was, however it would originally have behaved, our y values are going to get bigger twice as fast. So if this was our original function, this is our original function, sorry, if this part is our original function, it has a particular behavior. When you multiply all of your y outputs, when you multiply all of that by 2, your y outputs are going to get bigger twice as fast. Contrary to that, we have, or converse of that, if we multiply by a number less than, sorry, if we multiply by a fraction, effectively a number between 0 and 1, we are going to end up flattening our curve. We are going to rise more slowly because all of our y outputs from the original function have been subdued. They have been suppressed by a third. They're a third of what they otherwise would have been. So that is my yellow curve g of x here. All of my y outputs are a third of what they would have been. All of my y points are reduced by a third. And it gives the curve a very flattened, squashed appearance. The last one we have again touched on many times. We know that if we have a positive quadratic, we have a smiley face. If we have a negative quadratic, we have a frowny face. We have a sad face. And we remembered this all the way back from junior cert. But just to remind you, if you ended up with the very simple case, it's like h of x is equal to x squared and f of x is equal to minus x squared, that would effectively just mean that you got mirrored in the x-axis. That is obviously not true in general if you have, or sorry, that is true in general, my apologies. So if you have your functions and you just multiply them by minus, you mirror them in the x-axis. And that is the most general way of thinking about that situation. Now, let's have a look at a particular question. So if we have our function here, we have f of x is given to us here, and we're asked to sketch g of x, where g of x is equal to f of x plus 3, and h of x, where h of x is equal to minus a half times f of x. Now, you can figure out what f of x is. This is not too challenging to figure out in this case. So let's do a little bit of investigation and see what this function ought to be. So if I start off with the key pieces of information that I've got, I have my maximum point. So I have a maximum, I have a frowny face type function. Therefore, I have a negative quadratic. That's the easiest one to see. Next one is I have its maximum point at x is equal to 2. So I have when x is 2, y is 0. So a root of my function and then would be, or the minimum point is going to be that at x is equal to 2, so therefore x minus 2 is my repeated factor. So my function looks something like, change my color here, my function looks something like minus something on x minus 2 to be squared. Now, if I squared this out, what would be the coefficient of, you can do this out the longer way normally, I'm just giving you an example, I'm just playing this through with you here. If you squared out this bracket, you would end up with your constant in your function being plus 4. Minus 2 squared is going to give you plus 4 on the end when you multiply out this piece. So you'd have x squared minus 4x plus 4. So you'd end up with minus x squared plus 4x minus 4. So you'd end up with minus 4 on the end, but we don't. We end up with minus 2. So just like we've dealt with our roots before, we need to be careful of another point on the curve that gives us the exact function we are dealing with. So we can see that we've only gone half as much. This is what we would usually do with k, but in general, then we would have minus a half of x minus a half x squared minus 4x plus 4 would be a way of writing f of x. This is just to give you some intuition as to the function we start out with. So we have that to help with our intuition. So that's our original function, and that's how you can interpret what the original function is. Those are our ways of playing it through, just like we would have done already for getting the function from the roots. Now, if we wanted to know about f of x plus 3, the way that we would figure out how to draw that, or a way that we could figure out how to draw that, is to think about what's going to happen with our function here. So at the moment, y is equal to 0 here. If we had x plus 3, what's going to happen? Well, that means that we are going to end up hitting 0 at 3 units earlier. So we would go 1, 2, 3. Our function would hit 0 at minus 1. So that's how you can interpret what that function would look like. And again, this is what we have discussed here. We would end up hitting 0 3 units earlier. So that's what g of x would look like. Now, is there any point that we can link to? When we went across by 2, we went down by 2. So when we go across by 2, we go down by 2. Yeah, that point should be on our curve, and it's roughly correct. As so. So that would be g of x. And again, we get that by looking at the fact that our maximum should occur 3 units before it currently does, for the argument, the same argument as we have given over here. And then the final one, h of x, is minus a half times f of x. Well, that means that it is going to get mirrored. The minus means that f of x is going to get mirrored in the x-axis, so it's going to be a smiley face, and it's going to be multiplied by half, so it's going to rise half as quickly. So currently it crosses the y-axis at minus 2, so it should end up crossing the y-axis at 1. It's only gone up half as much. As so, that should be more rounded at the bottom. So that's a bit better. So more rounded at the bottom, and again, we can use our y-intercepts or any known point on the function to see that y should have increased only half as much as we go along. So that's how we can relate our different graphs together.